Dear friends, in the last lecture we have discussed about interactive and cooperative processes, critical section problem and semaphores. In this lecture we will discuss about various issues related with memory management. We will also discuss few memory management techniques such as fixed partition and variable partition. We are going to start with memory management. Nowadays, multiprogramming is an important component of almost all computer systems. Multiprogramming is used to improve the utilization of CPU and other input output resources. To implement the concept of multiprogramming, multiple processes are loaded into main memory and runs simultaneously. CPU executes each process one by one using any scheduling algorithm by accessing the instructions and data of the processes stored in memory. Every normal computer system has limited amount of main memory, approximately ranging from 1 to 16 gigabytes. One portion of the main memory is always occupied by the resident portion of operating system as shown in figure. Remaining part of main memory is shared among all the running processes. It is the responsibility of the operating system to distribute and manage the main memory efficiently among competing processes. The part of operating system which manages main memory is called memory manager, and this activity is called memory management. This figure contains an example of main memory loaded with multiple processes. One part of memory has been occupied by operating system. Three processes, process 1, process 2 and process 3 have occupied some portion of memory depending upon their size, and rest of the memory is free. Every process has its base address and limit value. In this figure, base address of process 2 indicates the memory address where the instructions and data of process 2 starts. Limit value of process 2 indicates total size of the process loaded into the memory. Here in this case, the process 2 can legally access all addresses from 300000 to 42000. The protection of memory access has been shown in this figure. CPU generates an address to access instruction or data of the running process. The CPU generated address is compared with the base address. If the address generated by CPU is not valid, that means less than the base register, it results in trap to the operating system. It means that the process is trying to access the code of some other process or operating system memory area. If the address generated by CPU is valid, it is compared with limit register. If the address is within the process size limit, it is clear to make physical memory access, otherwise again a trap to operating system is generated. Next we are going to discuss logical versus physical address space. Every program on hard disk contains some instruction and data. Each program takes some amount of hard disk to store itself, and that is called the size of the program, measured in kilobytes, megabytes or gigabytes. From a programmer point of view, every program starts from 0th location of the memory and ends up to the size of the program. This figure contains a program containing its data and instructions. The size of the program is 912K. The same program, when loaded in memory, it takes some space in memory from 1022016 to 1022927 and becomes a process as shown in figure. Now, if CPU refers to any instruction of this process, it will generate an address within the range of 0 to 911, otherwise it will trap. The address generated by CPU is called logical address, and the set of all addresses generated by CPU for a process is called logical address space of that process. During the execution of the process, if the logical address generated by CPU is say 512, that means CPU needs the instruction or data at address 512 to execute. The instruction or data placed at address 512 in logical address space will be at different location in physical memory as the process has been loaded at some different location and not at 0th location of memory. Therefore, to fetch the correct instruction or data required by CPU, the contents of base register, which is 1022016, will have to be added to the logical address 512 to generate a new address called physical address as shown in figure. The instruction or data required by CPU can be fetched from this physical address. The collection of all physical addresses corresponding to all logical addresses of a process is called physical address space of that process. To sum up, an address generated by the CPU is commonly referred to as a logical address, whereas the corresponding address seen by the memory unit is commonly referred to as a physical address. The conversion of logical address into physical address called mapping of address space to memory space. The mapping of logical address space to physical address space is central to proper memory management. Next, we are going to discuss various memory allocation strategies. When a computer system starts, it loads operating system in lower part of memory and other part of the memory is used to load user processes as already discussed. Memory manager allocates main memory among processes in the most efficient way possible. Broadly, various techniques to allocate main memory among processes can be divided into two categories. First is contiguous storage allocation. Contiguous storage allocation implies that a program's data and instructions are allocated a single contiguous memory area. It is further subdivided into fixed partition storage allocation strategy and variable partition storage allocation strategy. Second is non-contiguous storage allocation. This technique implies that a program's data and instructions can be allocated to scattered memory area that is not contiguous. This technique includes paging and segmentation memory management techniques. Next, we are going to discuss fixed equal size partitions. The basic memory management approach is to divide memory into fixed number of partitions, each of same size, where each partition accommodates only one process for execution as shown in figure. The maximum number of processes residing in memory will be same as the number of partitions. When a program terminates, one partition becomes free and another program can be loaded in that partition. In a fixed partitions technique of memory management, all partitions are of same size as shown in figure. All partitions are of size 512K. Fixed equal sized partitions are relatively simple to implement. However, there are two problems. This scheme is not easy to use when a program requires more space than the partition size. For example, if a process of size greater than 512K is required to load in memory, it will not possible. In this situation, the programmer has to resort to overlays. The second problem is internal fragmentation. Whatever is the size of the process, a fixed size of memory block is allocated to it as shown in figure. So, there will always be some space which will remain unutilized within the partition. Let us suppose that we have processes of size 460K, 500K, 70K, 230K. In this case, the memory allocated to a process which is 512K is slightly larger than the requested memory. The amount of difference between these two numbers is called internal fragmentation. It can be explained as a parking area consisting of equal sized parking slot for parking of big sized, medium sized and small sized vehicles. Here, if any vehicle of any size comes for parking and parking slot is free, the vehicle is allocated the parking slot. During this technique, it may happen that small size cars are using the parking slot big enough for bus parking. Two cars can have a space between them, but that cannot be used by any other vehicle. Hence, a lot of parking area may be wasting, causing internal fragmentation. Next, we have fixed unequal size partitions. In fixed unequal size partition technique of memory management, the memory is partitioned into fixed number of partitions, each with different sizes as shown in figure. Size of partitions are ranging from 128K to 1 MB. Processes are loaded into the partition of size nearest to its requirements. It is easy to always ensure the best fit. For example, if a process of size 200K comes, then partition of size 256K will be used to load that process. Processes with small address space use small partitions and processes with large address space use large partitions. One may organize a queue for each size of partition as shown in this figure. With best fit policy, fixed unequal sized partitions minimize internal fragmentation. However, best fit policy of allocation may be quite slow in execution. Let if we have processes of sizes 70K, 90K, 112K and 60K, then using best fit policy, each of these processes will try to load itself in a partition of size 128K. One of the processes will get this partition and others will make a queue to get the partition free. The disadvantage of sorting the incoming jobs into separate queues is obvious because a process may keep on waiting in the best fit queue even while the queue for a large partition is empty. Here, small processes have to wait to get into memory even though plenty of memory is free. An alternative arrangement is to maintain a single queue as shown in figure. Whenever a partition becomes free, the job closest to the front of the queue that fits in it could be loaded into the empty portion and run. Since it is undesirable to waste a large partition on a small process, a different strategy is to search the whole input queue. Whenever a partition becomes free, pick the largest job from queue that fits in this partition. In fixed unequal size partitions scheme of memory management, there is very less or no internal fragmentation, but process loading and unloading produces empty holes scattered throughout the memory. Having total space good enough to accommodate few processes, but due to non-contiguous scattering of holes, it cannot be used to store processes contiguously. This is called the problem of external fragmentation. The fixed unequal sized partitions scheme of memory management can be explained by taking the same example of parking slot. Now, let we have a parking area consisting of separate parking slots of unequal sizes for parking of big sized, medium sized and small sized vehicles. If all parking slots reserved for car parking are full, the other cars will have to wait until some parking slot for car gets free. If parking slot for buses are free, it cannot be used for parking of cars and remained unused. Next is variable partitions or dynamic partitioning. In this scheme of memory management, the whole memory for user processes is considered to be a big single partition. In this scheme, each process occupy only as much memory as required. Processes are loaded into the memory until entire physical memory is exhausted or remaining space is not sufficient enough to accommodate new process. Unlike fixed partition scheme, where whole memory is partitioned into fixed number of partitions in advance, in variable partition scheme the partitions used are of variable size and the number of partitions are not defined in advance. As the processes enter in memory, they are allocated contiguous memory area and base address of the processes and limit value of processes are stored in partition description table called PDT. Unlike fixed partitions, here the number of partitions keep on changing. That means degree of multiprogramming can change dynamically depending upon the size of the processes. Therefore, the base address of each occupied partition and unoccupied partition keep on changing. When some process terminates, it frees its memory and a free portion, also called hole, is created which can be used to load another process. We can understand the concept using this example. This figure shows the allocation of processes in different stages by using variable partitioning method. Here the available memory size is 1 MB or 1024 KB. Initially the main memory is empty, having only the operating system loaded in it as shown in figure A. Then process 1 of size 350K is loaded in memory as shown in figure B. Then process 2 of size 400K is loaded without any gap and the remaining free space in main memory is 146K as shown in figure C. Process 1 is swapped out for allocating the other higher priority process as shown in figure D. After allocating memory to process 3 of size 300K, a hole of size 50K is created as shown in figure E. Now process 2 swaps out as shown in figure F. Process 1 swaps in into this block leading to a hole of size 50K shown in figure G. In this fashion, multiple holes are generated in memory. Ultimately, memory becomes more and more fragmented. The total memory occupied by all holes may be sufficient enough to load few processes in memory, but it cannot be done as the memory space occupied by holes is not contiguous. This problem is called external fragmentation. Sometimes there may be a situation when multiple holes are available in memory and size of these holes is more than the size of incoming job. In this situation, allocation of holes to incoming program can be done using different strategies. The set of holes is searched to determine which hole is best to allocate. First fit, best fit and worst fit are the most common hole allocation strategies used to select a free hole from the set of available holes. First is first fit. Using this strategy, we allocate the first hole to incoming process that is big enough. Searching can start either at the beginning of the set of holes or where the previous first fit search ended. We can stop searching as soon as we find a free hole that is large enough to load the incoming program. Best fit. In this technique, allocate the smallest hole that is big enough. We must search the entire list unless the list is kept order by size. This strategy produces the smallest leftover hole. Third is worst fit. Using this technique, we allocate the largest hole. Again, we must search the entire list unless it is sorted by size. This strategy produces the largest leftover hole, which may be more useful than the smaller leftover holes. One solution to the problem of external fragmentation is compaction. The process of compaction shuffles all holes in one large hole. Compaction is not always possible. Dynamic movement of processes from one memory allocation to another memory location is not always feasible. It depends upon the situation whether memory allocation is done at compile time, load time or run time. Compaction is possible only if relocation is dynamic and is done at execution time. If addresses are relocated dynamically, relocation requires only moving the program and data and then changing the base register to reflect the new base address. When compaction is possible, we must determine its cost. The simplest compaction algorithm is to move all processes towards one end of the memory, all holes move in the other direction, producing one large block of available memory. This scheme can be expensive. Finally, we have conclusions. Memory management algorithms are required to implement multiprogramming. To provide protection, every memory address generated by the CPU must be checked for legality and possibly mapped to physical address. All memory management techniques can be divided into two categories, that means contiguous storage allocation and non-contiguous storage allocation. Contiguous storage allocation techniques include fixed equal size partitions, fixed unequal size partitions and variable partitions. Each of these memory management techniques has their advantages and limitations. Thanks.